And thank you. I'd like to thank the organizers for the opportunity to address this workshop regarding our work on temperature imaging with ultrasound, imaging temperature change, in fact. And I use the terms thermography and thermometry right now because thermography is kind of more like B-mode ultrasound with temperature imaging. We make some assumptions about the tissue properties, and you get what you think is a temperature map and change. But we think now we're ready to start moving more in the direction of thermometry with the same technique. It will require some knowledge of the source and maybe some characterization of the tissue, which is what we're working on right now. But we're very excited about the in vivo data that we're able to obtain, which I think validate or some of our modeling without a doubt. Just a little bit of housekeeping. Some of this work is supported by a company that I'm consulting with, and I'm required by the university to put these things. Obviously, the work that I'll present is really there is some history behind it. Ralph Sipe at Philips and Claudio Simon, both of them at Philips now, started this work in the 90s, and the model that most people use, and some authors like Dr. Kang yesterday referred to this as thermal strain, is based on our modeling that we introduced in the 90s, and other people have contributed to this work. And also the work is collaboration with Dr. Bischoff and Dr. Chrisman from our radiology department. Just in terms of motivation for what we're actually trying to do in this area, there is a great deal that has been accomplished in the last few years. I really liked the historical perspective that Mikhail put in terms of ultrasound. The same you can imagine happened. We started doing phased arrays in the 80s, and the control was very coarse. We developed these nice algorithms for refocusing arrays, but the circuitry, just simply the error in quantizing amplitude and phase, for example, for phased arrays was larger than anything you can hope to correct. So now we have very, very fine control of phase and amplitude. We have very fine control of spatial and temporal dynamics of heating as well as imaging that's happening on this side. Also the technology in terms of both GPUs and FPGAs have made great impact on ultrasound imaging and therapy. And these are allowing us to resynthesize patterns in real time. We've published this result with millisecond resolution. So we actually compute based on a method that I, for my thesis, was worked on what we call pseudo-inverse pattern synthesis method with multiple focus. We can resynthesize at 1,000 times a second. So that's thanks to the circuitry and the new high-performance computing structures that are available. And again, like was mentioned by Mikhail and Jürgen, we are doing software beamforming, completely software beamforming for our synthetic aperture imaging. So we can do a lot in terms of control. The feedback is an issue that is still kind of out there, especially in terms of highly specific feedback to tissue excitation and so on. And again, all of this is in the context of image-guided HIFU therapy. I'd like to kind of limit to that, but it does apply to other forms of non-invasive or minimally invasive surgery. So for example, we have, over the last couple of years, we have demonstrated the use of real-time ultrasound for thermography. We have a couple of papers, both on the basic platform to do this, but also more recently this year, the real-time control, and I'm going to show some results of that. So here, for example, we're actually doing this at hundreds of frames per second. This is very important. I'm actually in full agreement with Mikhail on the fact that you need to do this and acquire the dynamics of the tissue as fast as you can. We made a determination for thermal imaging that we need to just at least to capture the tissue deformation so that we can have the full time history of both tissue motion and deformation as well as the actual temperature-induced change. And we found that something like around 150 frames per second is reasonable to capture these types of tissue deformations. The idea is that if I can capture them, I can separate them from actual temperature changes. And with ultrasound, this is a unique advantage of ultrasound. We have demonstrated from early on that we have a sensitivity of really a small change in temperature, 0.1 degree in a kind of a static tissue. We can pick quite nicely. For example, that's not the case for MR. You need much higher baseline, change in baseline temperature to actually detect. And also there is sensitivity to motion. So the advantage of ultrasound is that it's very sensitive, and also, of course, both the time and spatial resolution that's exquisite in our case. In terms of motivating some of the things that I'd like to discuss today, one of the things that has always been near and dear to my heart in terms of temperature imaging is that I'd like to use temperature imaging at sub-therapeutic level for cause a very small focused heating of the tissue, characterize that heating spot that I'm actually focused in the same direction, measure the tissue response to that focus before I actually apply the high-intensity focused ultrasound suitable for therapy. So this is like training your gun. You're trying to see how the tissue responds. Are you directing the energy? So that's the challenge, and that's the kind of thing that MR, for example, will not do. This is not against MR. As I was talking to some of my colleagues here, MR is great for certain things, but this particular application of HIFU really requires ultrasound temperature imaging. And I'd like to share, today we'll share some of our in vivo data that demonstrates that this is doable with ultrasound. So again, the characteristics of a HIFU beam is that small size, but also short duration. The HIFU shot is typically 1 second or even less for coagulation. And we'd like to detect that in subtherapeutic mode. So the high frame rate, and again, it's all relative. My high frame rate at this point is in the hundreds of frames per second. We'd love to go to the thousands if that's necessary, but for this approach, we're trying to maximize the frame rate to capture the tissue motion deformation so that we can try to separate them. So that it's, as you'll see today, it is kind of a needle in a haystack. And the beauty of ultrasound is that you really can't find that needle, regardless of that. So just a very little bit of history here. We started working on the temperature imaging of the ultrasound in the 90s. We have assumed that the scattering of tissue is based on a kind of a semi-regular lattice, which led to really 2 models that we published early on, that you can use reflection mode ultrasound to detect small changes in the echolocations that are indicative of temperature change, but also small changes in the spectrum. And both of these techniques can be used. They are obviously related, but they lead to different artifacts. In 2005, we put a paper that actually talked about combining these 2 techniques, for example, for better estimate of temperature. If there is a required equation, I'm not sure, but I'll just show these simple equations. The time shift method, the change in echolocation, you can see there's a proportionality between the change in temperature to a speed of sound and a material constant. That material constant is related to both the thermal coefficient of the speed of sound and the coefficient of thermal expansion. Depending on what is the baseline temperature, like at 37 degree, the thermal expansion is about 1/7 or so of the speed of sound change. But as the temperature changes, the thermal expansion becomes more important because the coefficient of the speed of sound is reduced. And this term led some people in the field to call this thermal strain. I really don't like thermal strain, but what can I do? I don't have control over the whole field. But this is basically you're taking a derivative of the accumulated shifts in temperature. You're taking a derivative in the axial direction, which people refer to as strain. Similar formula we were obtained in terms of the temperature change for a change in the spectral peaks that are related to the mean scatterer spacing. I'm going to focus on this method today. And we have worked very hard in the last few years to put together our own system that allowed us to perform these types of experiments in real time. Temperature, so for example, here there is a single element HIFO transducer focused into the sample. In this case, for example, a hard sample. The heating is right here, and this kind of result is obtained in real time. The data is collected, the RF mode, sampled at 40 megahertz through a gigabit interface. All the processing happens on a GPU on this computer. Basically, you compute the speckle tracking result using cross-correlation, complex cross-correlation technique, and then you differentiate in the axial direction, plus some simple 2D filtering. So this is the heating spot, and this is the time history of the heating spot. Nice textbook change in as you start the power on, you have exponential growth and decay. This is a typical result. This is something we can get on a daily basis. Those of you who have visited our lab may have seen something like this, either in vitro or that happens every day. Dr. Delonglu, currently with Philips, has put this system together. It allows for real time. We call this M2D for Dr. Tantar explained that, for example, if you want to improve the frame rate, you can reduce the number of lines with conventional ultrasound. That's exactly what we do. But the idea is that we want to work at sufficiently high frame rates in the 100 frames per second to achieve the fine spatial and temporal resolution that allows us to do some of the signal processing that's needed to extract the temperature data. This is not intended to confuse, but also we have designed a reconfigurable pipeline architecture for what we call integrated experiment platform. The platform basically interfaces with an existing engine. This is a Sonics RP. It could be a Visual Sonics and so on, but we only use this to collect the ultrasound data, nothing more. All the processing happens in here, and you can invoke a number of platforms with a GPU. If you're in development mode, you can use MATLAB, you can use computation and so on. And this architecture allowed us to really have maximum flexibility in terms of development of techniques. So in a typical experiment, everything happens in real time. You are controlling a phased array for heating, an imaging device like this, collecting the data so it happens in front of your eyes. But also, you can, if you're developing something and you need MATLAB, it may slow down your operations for certain tasks, but it's obviously more flexible. So typically what we do is we start here, and then as we become more confident this is what we want to do, we move to a more real-time implementation in terms of GPU platform. Some of the things that we do, for example, in MATLAB, is that we have developed a post-processing filtering scheme which is inspired by the bioheat equation. Here is actually where the higher frame rate was extremely helpful. So as I acquire the data, both in space and time, with high spatial resolution, I should mention my temperature calculation is computed at every pixel of the RF data sampled at 40 megahertz. This is in real time. So you collect both high spatial resolution and high temporal resolution. This allows us to do rather sophisticated 2D, in fact, in this case, 3D filtering, combined with a projection algorithm that kind of forces the data to conform, if you will, with temperature evolution according to the bioheat equation, which is the known model for, and this is nothing more than the Green's function of the bioheat equation. So this is actually implemented in real time as a 2D filter. And I'd like to show some of the results. These results are minimally processed, and they show some of the artifacts, but that's actually by design. We want to show what's happening. So this is an experiment where we're using a dual mode ultrasound array, And then there is an imaging transducer that's looking coaxially or registered coaxially with the therapy transducer. We're doing a subtherapeutic pattern, so we're trying to heat for 1 or 1.5 degree. As you can see in here, you'll see the linear scale as I run the movie. And this is a localized focus. The geometric focus is about 40 millimeter from the array, so we're shooting ultrasound this way. And by the way, these are static, but these are axial, temporal, and lateral temporal images, if you will, of the heating pattern. But let me play and show you the kind of things that happens. So this is baseline before we start heating. We're going to start heating right now. You can see I'm actually monitoring right at near the focal point in here where we're focused. This is actually prefocal heating, but there are some artifacts that I keep in here. But if you look at the temperature rise and decay, that's consistent with our source. And this is what we're excited about, that now we are seeing in vivo those algorithms that I explained earlier. That's kind of a validation that this model is not just in a static or in a phantom result. So, but at the same time, there are still challenges. That is, you can see some things. There is actually a blood vessel around here, so you can see some artifacts. Now, if you look at the time history of what happens here, there is no way you can mistake this for temperature. But this is the kind of thing that we still need to work on in terms of the temporal processing. I'm mostly doing spatial processing. But the heating is exactly what you expect it to be. There is some prefocal heating just under the skin. In fact, we have done histology that showed when we went to HIFO, I don't have these slides here, but there was actually damage in these regions, indicating there was, in fact, prefocal heating. So in a real treatment, you see this and you see this, and if it's really temperature, then you know that you may be in trouble in terms of heating something that you did not intend. This is really our goal. We want to kind of check the HIFO pattern before our scalpel, if you will, before we cut into the tissue in terms of surgery. And this is an example of baseline temperature. So there is no heating in here. And this is what the tissue response, as you can see. So there is actually, in these experiments, the rats were under deep anesthesia. So they basically gasped every 1.5 seconds. They would just simply reach for air. And these are the results of these gasps. Again, you don't mistake this for temperature. But this, if you can see here, the baseline, the change in temperature due to these events is on the order of 0.2 degree. So what we are actually suggesting is that we can detect changes in temperature on the order of 0.1 and so on. But right now, based on what we're doing, this identical signal processing to the data with heating that I showed before, and it shows that there may be other motions that we cannot remove based on this post-processing scheme that I indicated, but it's on the order of a fraction of a degree, as you can see, 0.2 degree, when the temperature change was on the order of 1.5 degree. This is another example that I want to show, which is actually the beam here was modulated with sinusoidal modulation. So as we heated, we also created an ARF, but what I'm showing here is actually showing the temperature data according to the post-processing scheme that I indicated with the bioheat-inspired filter. And this is about 15 hertz. The data in here is 15 hertz, the modulation, and it's completely eliminated. But if you look at the spatial resolution of the heating spot, it has not suffered a bit. So we're able to remove the temporal variation of 15 hertz, which is also consistent with some of the natural motions, without affecting the spatial resolution. That's the beauty of this bioheat-inspired filters, that we're actually filtering, but we're not making the temperature field so diffuse. You're not losing resolution. So that's the point of this result. This data has an artifact in here. Sometimes you have motion. Again, if you looked at the time history around here, it just simply is a change, but because of the accumulation of the delays. So my point, again, of keeping this example is to show you that when we actually look at the time history, it's very easy to see temperature change versus transients and so on. We have not removed this, and we're still working on these types of techniques, but we still have valuable information in terms of the time. So we have done some work on Kalman filtering, for example, for tissue property measurement, that we're actually employing this area to get to kind of basically get a pure temperature map of these types of things, including some of the feedback that you can see in here. By the way, if there are any questions, maybe I can answer here, because I'm going to switch gears to some of the applications. Yes?
From what I saw from your equations, your construction depends on this parameter k.
Yes.
How much variation is there in between different people? Because you need to know this parameter.
That's an excellent point, and that's really one of the main limitations of ultrasonic techniques, that everything that we do is tissue dependent. So when we do things in the lab, whether both in vitro tissue, we have characterized fully, like heart muscle, liver tissue, and we have the exact parameters, and we have comparison with thermocouples, and it works exactly right. With tissue, I do need better anatomical imaging, and I'm going to show just an example of a cross-section of the kind of tissue where the muscle groups and so on. So I need to know a little bit better, have a better estimate of this parameter. Everything that I've shown was based on an assumed tissue parameter model. This is all thermography. Just like we say speed of sound 1500 meters per second. It's not really 1500. It changes a little bit. The change is quite small. I'm sorry. So the different tissues is quite small. The point that was made yesterday is an excellent one. The fat tissue behaves differently. So that needs to be, so for example, if I have a characterization of tissue, some of the things that Bill talked about today is fantastic. If I can recognize this as fat, then I can account for it locally. The beauty of this is all local, so it's not accumulated spatially. So we can account for the variation in tissue by better anatomical imaging or better recognition of the region that we're imaging, if that answers the question. There was a question here? Yes?
Is there a way to verify that the temperature that you measure using the apparent strain or thermal strain is actually the temperature? Is there a way to verify?
Yes, actually we have thermocouple data that corresponds to these types of experiments. And we have a publication coming up. We're going to show this. That's why I'm excited about what I'm showing, is that finally I can say with complete confidence that I don't like thermal strain, that, that thermography data, as we described it, is in fact temperature data. It's nothing else. So, and we have thermocouple data that corresponds to that. We'll show it in the same type of rat experiment. So that's happening, and you'll see it very soon.
Have you done any measurements on tissue tumors, benign versus malignant, determine whether malignant tissues have higher rates of blood flow, higher temperatures in them?
I love this question. We have not, but one of the applications of what we do today, because we can very reliably at the focal point measure both the heating rate and the decay rate. We'd like to measure perfusion, for example, based on decay rate, and also the diffusivity based on this kind of curve. You see the change in this is actually relates to the blood perfusion. So we'd love to do that. That's, this is my collaboration with Dr. Bischoff. He has an excellent, in our mechanical engineering, biomedical engineering, he has an excellent small animal model cell injury lab. And we're going to be working with this as part of a new proposal that we're putting together. Thanks. Yes?
I was wanting to know, really just to measurement,
yes.
How can you resolve the difference, the huge difference, it's double between fat and tissue?
Yes.
And if there is like the initial state, it could be subcutaneous, it could be double because of the subcutaneous fat, which has slowed down.
Right. So right now, this is all thermography this does not distinguish between, so I apply the same constant to everywhere. This is like an ultrasound image. The only difference that I'm actually doing this, as I indicated, at like pixel size and very fast, so we're capturing all motion. Now, these have artifacts in them. The next step is to start accounting for the local tissue structure. Some kind of tissue characterization, like Bill suggested, will be the key, whether it's fat or other tissues, that we will try to characterize the tissue or some knowledge. So, for example, we have begun to use histology data and correlate with ultrasound displacement data, where the boundaries between muscle groups are very clear, unmistakable. You would not guess it before, but once we have the histology and we also have some MR, it's very clear. So now we have a sense of where these types of aberrant shifts, the aberrations and shifts, if you will, they start to show, and that's our objective right now, is to start to become more specific. We have the sensitivity, that's what I'm showing today. The next step is specificity. And that has to be both anatomical imaging to recognize where we are, but also more constraints on the evolution of the temperature. I can tell you, I am already expanding this idea of bioheat-inspired filtering. It's actually now an evolution equation based on the bioheat equation itself. So that's coming. Yes?
This is really neat. I have a quick question. You mentioned earlier that you had fully steerable IFB.
Yes.
Correct? And so that kind of looks like a collimate beam. Are we steering here, or what's going on?
No, actually it's not. The focus is right here in the image at about 40 millimeter.
Oh, it's just here.
And so what you're seeing a lot of artifacts. So this is actually prefocal heating. This is actual heating.
Okay.
And here there's a blood vessel.
I see.
Yeah, and this is boundary effect at the edge of the data. So I can tell you every one of these what kind of an artifact it is. We have not really shown this nice clean heating pattern.
There are artifacts, not heat.
This is actual heating. This is artifact.
Gotcha.
Yeah, but it's known where it's actually a pulsating blood. We can see the pulsation, the blood vessel, and so on. So if I had the time, I would explain every aspect of this image. I can tell you where it's coming from. So we know. Now it's a matter of algorithmically starting to deal with these things. So it brings me to the next slide, which says, this is only the beginning. We really are just starting. And, we've been doing this for a number of years, but finally that I have all these displacements, now I think we're ready to do some meaningful work in terms of temperature imaging. So for that, I'd like to show you today some of our real-time control of temperature, both spatial and temporal, and then also the quantitative tissue property measurements and real-time thermometry that we're actually now proposing for the NIH, I hope, soon. So the other part of the story, to kind of demonstrate what we're doing, something that we're excited about, we also built a system in our lab that allows for a unique paradigm in image-guided surgery, where the therapy array is also your imaging array. And while the therapy array may not give you the highest quality images, it gives you the highest specificity imaging as to what the HIFO beam is trying to do. So this is Andy Kasper. He's actually doing his oral prelim next week. Fantastic student who worked with DeLong Lu to implement the DMUA controller. And this is his demonstration of the future of surgery with ultrasound. The beam is actually being resynthesized on a frame-by-frame basis. This is a kidney, an image of a kidney in vitro, imaged by, is this guy? Yeah, it's moving. So baseline, now we start heating, and you can start see changes in echogenicity as soon as the HIFO beam, and then there's also a boiling event that takes place. So this is what the doctor will be able to see with this kind of system. Immediate feedback on the dynamics of lesion formation, and at the same time you can superimpose your beam. You can see where that scalpel is working momentarily. In fact, you can account for distortion to the beam due to rips and things like that in terms of the computational model and the resynthesis. As I indicated, this is done at 1,000 frames per second, the kind of recentness that takes place. So this is a system that we've been using in some of our experiments. I want to show today a control experiment, which actually we're planning to use in a new grant that we have from the university on image-guided drug delivery, targeted drug delivery application. I don't want to bother you with the control strategy. Everybody may be familiar with PID type control, but we're imaging with a diagnostic transducer and using a DMUA, dual mode ultrasound array, to focus at multiple points and simultaneously control the field based on non-invasive temperature feedback or ultrasound thermography. And this is examples of what you can do with an array. As you can see in here, single or multiple focusing. We have the flexibility of controlling the field at one thing that we worked out, and it looks like I may run out of time, the power dynamic power reallocation. We do multiple focusing. We can optimize the power going to either of the foci, maintaining the supply power within the limits of the supply power. And let me just run the experiment. It's a double focus experiment. The DMUA is here. You see we've used two images. One is the diagnostic image, B-mode image, and this is the DMUA image, so we can recognize the target. See, this is baseline. The field is on. We're heating at two foci. One of the foci reaches the set point, so the power is reduced, while it continues on the other. Now the second set point is reached. This is all based on non-invasive temperature feedback. On the left, you see the thermocouple measurement, and in blue, and the ultrasound thermography measurement in green. What's this? For the experienced hyperthermia, Bob McGuff, you're still here. Thermocouple artifact. Okay? And that's because we introduced, after we reached the set point on the first one, we actually increased the power, so you can actually see that thermocouple self-heating artifact in here right away. So it's exciting for us that we can do this. We can actually get even less artifact on the non-invasive data. So this is the future, I hope, of surgery. This is just a quick explanation of what happens here. Why am I excited about this? Because the kind of corrections from frame to frame is very small change in amplitude, very small change in phase. And it's because of that new driver that we're able to achieve these small changes. And that happens dynamically from frame to frame as the controller asks for different change in amplitude. So we can map anywhere in this space with very high precision to maintain very high precise control on the heating pattern. Just to show you that this also works in tissue, this is in a kidney experiment, single focus, but just to make the point. And you can see the control, the set temperature, and the control temperature. Again, this is calibrated. We know the thermal properties of the tissue and so on. So we're actually not only doing thermography, but thermometry in this case. This is real temperature. Minor point regarding the power reallocation. Why is it important? I reach the first set point, then I'm able to allow more power at the second focus for the second one. If I didn't do this, it takes me a longer time to reach my set point. So it's an optimization way that kind of minimizes the treatment time and improves your ability, both in space and time, to control the dynamics of a surgery experiment, thermal surgery experiment. Just to answer one of the questions, even in a very simple rat leg experiment, these muscle groups, they're probably experts in this room, much more expert on this, but when the rat gasps, for example, these muscles do not move exactly together. And they're like nodes that seem to have more deformation, more strain than others, right? So these are the kind of things that we need to start accounting for in terms of more localized heating, understanding. So it's not just the fat, it's the heterogeneity in the tissue in general, but also the heterogeneity in the deformation model. And that's exactly what now that we have the tools, we've been working on this for many years, but we never had a complete look at the dynamics of the tissue as we have now. And to my mind, with all due respect to everyone in the field, you have to have something like this in order to be able to solve the temperature imaging problem. There's no other way. And I think that's, it just leads to, going back to the architecture that we talked about, I'd like to incorporate more computational components in here. So for example, if I'm looking at an image, if I'm looking at an image like this, and if I'm able to account, maybe I can compute the field, I can use my Kalman filter strategy, for example, to get exact thermometry data. So that requires some computation online, or at least either in real time or online, so that the doctor maybe can do a quick calculation that may take 30 seconds for determining on the next shot. So that's kind of our vision of the future, is that you would be collecting imaging like this, perhaps doing some experiment like that, and then doing some computation to adapt in real time to what you're imaging. So like Mikhail, he had to leave, mentioned, we're not going to just simply do pulse echo. Our imaging will also be adaptive to better characterize the regions that we're in. So I'm sorry if I've taken more than the allotted time. These are my conclusions. Certainly for subtherapeutic beams, we can localize these both in space and time in a unique way. I don't think there's any modality that matches ultrasound in this regard. And we're able to do this with sub-millimeter accuracy, as well as with high sensitivity. So a small change above baseline, typically 2 degrees or so, or even 1 degree, is sufficient. The idea of using physics-based filtering has been at least partially validated. We're actually working on the full implementation of that in terms of using the bioheat equation as a governing model. In fact, when I dream, I'm thinking of Navier-Stokes equation fully for these types technique, now that I have the full dynamics of the tissue. That's kind of what you've seen today. So also you've seen example of robust real-time control of multiple focus pattern, which is kind of what this technology is promising as a whole. Thank you very much.
We have a few questions in the middle, but there are a couple of questions now.
We thought about control systems for reshaping or relocalizing the beam for any kind of parts that get heated up that you didn't expect to get heated up, and the beam's not exactly.
Yep, exactly. So in our 2010 paper, we have talked about adaptive refocusing for transthoracic. So for example, you're trying to go to liver tumors. And this is what I showed from Andy. He actually can put the ribs anywhere in the image, and he can refocus and reshape. So there is a 2010 paper. I can email it to you, but it shows the adaptive refocusing, and it's based on either additional heating or something you can recognize on the image. So that's part of what the beauty of this system is, that this can be done again in real time.
Okay, one more.
This will be matched with human hypo treatment.
Absolutely, well, that's what we hope.
Exactly. Yeah, hopefully.
Yeah.
What is the temperature? When the temperature maybe increases above around 10 degrees.
Yeah.
So is this the equation solve this solve the problem of linearity?
No. So everything I said is valid for about 14 or so degrees. We've done all kinds of experiments where we heated about 14 in vitro and in vivo. We tracked very nicely. Above 55, there is a break in the speed of sound. So I was talking to some colleagues here today. We're actually relying on the thermal expansion component, and our 2D speckle tracking technique, we published also that result, will allow us to, instead of tracking the full combined thermal expansion speed of sound, we're going to rely more on thermal expansion from that point on. Mikhail also is not here, but he developed a technique for actually following the elastic modulus, and that's something we can easily extract. So if you go beyond 55, the speed of sound model, you know, the delta beta by delta t actually almost becomes 0 and then it's negative. So you can't continue to track. So you have to either go to the thermal expansion or some other parameter.
Let's thank the speaker again.
Thank you.